Thank you for coming. We're here today because there's a paper that was issued from the journal Nature today about the Sumatran earthquakes that happened last year. And you may ask, why should I care about an earthquake that happened more than a year ago? And why did it take you so long to figure it out? But it's common in the United States that after an earthquake, it takes on the order of several months to actually analyze the data. It's harder actually when the data are coming from a place as far away as Sumatra. So it took quite some time to collect the data and to analyze it and so on. We commonly also have media conferences after significant papers are published in Nature or published in Science magazine. And so I thought what we would do is try that out today here in Singapore. I invited my Indonesian colleague also who worked with us on this, but he's actually in the field today and unable to join us. So what I thought I would do is, if you take a look at this paper, you'll find it's fairly turgid. It's very difficult to understand, as Jacqueline, who tried to write the media release for it, found very quickly when she started reading it. But let me just go through with a few illustrations then to show you basically what. Oops, wrong one. To show you basically what we're talking about in this particular paper. And then at the end, there are maybe 10 slides or so. And then at the end, if you have any questions, you're welcome to ask. So let me just start with this. Here is Sumatra from the air with the ocean removed. So you can see the submarine environment in blue. And you can see that these islands are sitting out here offshore Sumatra. Here's Singapore, here's Jakarta, and here is the island of Sumatra about 2,000 kilometers long. This particular place right here is where the Indian plate begins its descent beneath Sumatra. So by the time, this plate here, this surface actually goes down, dives underneath Sumatra, and by the time it gets to here, it's about 20 kilometers beneath the surface. By the time it gets to here, it's about 100 kilometers, and by the time it gets to here, it's about 150. By the time it gets to Singapore, well, we're not even sure it's beneath Singapore, but it would be on the order of 1,000 kilometers or more below Singapore, and not seismic beneath Singapore. But this uppermost part is actually seismic, and it produced the earthquakes last year. So the contact between this plate and the overriding Sumatran landmass is called the megathrust. It's called the Sunda megathrust, after the Sunda Straits here where Krakatau is. So on this map, the barbed line is the megathrust where it begins its descent beneath Sumatra. And its first 100 or 200 kilometers of descent actually ends up being largely seismic. So what we're going to talk about today is this little patch that's shown here in these bright or warm colors. For about 15 years, my group and I have been studying this particular part of the Sumatran megathrust, the Sunda megathrust. And what we've determined, in short, is that the areas shown in warm colors are locked. And what that means is that the megathrust, as it goes down, gets stuck. As the plate goes down, it gets stuck at the megathrust. And so it takes Sumatra down with it. And then eventually, that stuck part becomes overloaded, and it springs back, and that produces a big earthquake. So the places where it's colored with the warm colors are places where we've defined it. We know it's stuck here and also up here. And places where it's lighter colors are places where it's not stuck, where it's sort of smoothly greased, if you will. So we've known for some time that, in fact, this large patch that we call the Mentawai patch, after the names of these islands, we've known it's been locked. So it was no surprise, actually, in fact, this last September when part of it broke. Now, we've used corals to figure out that, in fact, the last time it broke was here in 1797. Roughly this patch broke. And then in 1833, it broke again, 35 years later. So the whole thing basically ruptured last 175 to 210 years ago and has done nothing since. Okay, so what we've found is that, in fact, in 2007, in September 12th and 13th, this part of it broke right here, the part outlined by this blue, and also 12 hours later, this 7.9 occurred. All right, so here we have a 7.9 and an 8.4 compared to about an 8.8 and a 9.0. So the basic finding of this paper, the most important finding of the paper, is that what happened last year, even though they were big earthquakes and they scared the daylights out of people living there, and there was even a damaging tsunami, 2 damaging tsunamis, that only a very small part of this patch broke. All right? And so the question that remains, which we can't quite answer today, is when will the rest of this go? It turns out that these earthquakes added up, the slip during these earthquakes added up is only about a quarter or so of what happened during what's been stored since the last big earthquakes 175 to 210 years ago. So let me just show you a little bit about how we do this. Here's a GPS station that's permanent. We embed this in the ground on this tripod, and it actually talks to a satellite and beams the data down to us. And this instrument can measure to the nearest millimeter or centimeter or so how it's been moving, how things have been moving. All right? Now, we also, right after the earthquake, we got into a helicopter and we flew out of Jakarta and we made a very quick survey, partly to collect data that wasn't telemetering properly, but also to measure the uplift that we knew would have occurred on the reefs. So, for example, here's a little island. Before the earthquake, that was the beach, okay, and this was the coral reef, okay, and it was living. At the time of the earthquake, it rose about a meter, and the whole reef came out of the water, and all the corals died. So here, for example, is that reef. Here you can see all these corals that just days before were living in beautiful colors, and if you've gone snorkeling in Thailand or someplace, you've probably seen this sort of thing. We can actually measure how much uplift occurred, and from those measurements, both with the corals and with the GPS, we can tell what happened on the megathrust. We can tell how much it moved. So that's what I'll show you in just a second. Here, for example, is my graduate student, Aaron Melsner, and he's standing next to a coral. This was low tide before the earthquake. The coral could not grow above that low tide level. So here we have ways of measuring the vertical deformation using natural things like corals. So here's what we found. If you take a look at the GPS instruments, one here, one here, one here, every place where there's an arrow, there's a GPS instrument. And what we found is that, especially in this region, there were very large motions seaward towards the Indian Ocean. So these islands actually jumped out. You can see here's a 50-centimeter scale bar. These islands jumped out about 1.5 meters. So, and that happened within about 30 seconds. So we can see in our GPS measurements that there was about 1.5 meters of motion in about 30 seconds or so. Okay, and it's that motion that actually is related to the earthquake. Singapore would be about right there. It's not on this map. All right, now here in the vertical, here are the same islands, right here and here. And you can see that the vertical measurements made by both the corals and by the GPS instruments show that the islands, for the most part, came up. Okay, and they rose. Here's the scale bar again. They rose as much as 1 meter or so. In fact, 1.5 meters over here. Okay, but notice the mainland coast dropped down here and here. Okay, so the islands came up and the mainland coast went down, and that tells us a lot about what happened on the megathrust below. So we use these data plus seismological records plus some data from a Japanese satellite that tells us about how things moved, and we came up with what we call a model. And the model is how well the model fits the data are shown here. The red shows how well the model fits the coral data, and the green shows how well it fits the GPS data. This is the vertical. Now here's the horizontal. The horizontal data, you see the model in green fits the data very, very, very well. So let's see what that model is. Here's what actually happened during the earthquake. What happened is that this particular patch, this is both earthquakes put together. In fact, it's 3 earthquakes, an 8.4, 7.9, and a 7.0, all within 15 hours. Most of this is the 8.4. Started here and ruptured up through here. Okay? And you can see by looking at this scale bar that the amount of slip was on the order of, as much as 4, 5, 6 meters. Okay? So over 100 years or so, we've stored up many meters of slip, and during the earthquake, some part of that was relieved. And this also was a small amount of slip, less than 1 meter or so. So now let's see what this means. It's really clear from our analysis. Now, this will be my last slide, but I have others if you want to look into detail about the earthquakes, and we'll put this on the website so you'll be able to get more details if you want. But to be merciful, I thought I'd keep it to just this number of slides initially. So here's the here's the first earthquake, the 8.4, and its rupture. Here's the 7.9 here, and in fact, the